Hello everyone. First of all, I'd like to say thank you for this opportunity. My name is Candra and I'm from Padjadjaran University, Indonesia. Today, I'd like to tell you about my research with the title of comparison of direct and covalent gold nanoparticle immunoglobulin Y conjugation in lateral flow assay for SARS-CoV-2 receptor binding domain detection. As we all know, COVID-19 has been a pandemic that has spread throughout the world, and it's caused by SARS-CoV-2. Up until 28 July 2021, there's actually more than 195 million cases worldwide with the casualties of more than 4.1 million. And in Southeast Asia, there's actually more than 37 million cases with the casualties of more than 500,000. COVID-19 is easily spread throughout the blood and it has a common symptoms such as fever, dry cough, and fatigue, which is so hard to detectable, and so we need a diagnosis method in order to detect them. Up until now, RT-PCR is the gold standard for COVID-19 diagnosis, but it's time-consuming, expensive, and it requires special equipment, and so RT-PCR is not suitable for the large-scale population screening, and so we need to find the alternative for the large-scale population screening for COVID-19 detection. Lateral flow assay is one of the best alternative method for the large-scale population screening because it is achievable and fast to detect. It's meet the assured criteria, which is affordable, sensitive, specific, user-friendly, robust, and equipment-free and deliverable to end users. But there's one point that has been a major concern for the lateral flow assay, which is the sensitivity. And there's actually many parts of the lateral flow assay, such as sample pad, conjugate release pad, membrane, test line, control line, baking card, and absorbent pad. But in this research, we will optimize part of the conjugate release pad, which is the gold nanoparticle and antibody conjugate, which determine the sensitivity of the lateral flow assay and is one of the most important part of the lateral flow assay. For the antibody, we'll use IgY or immunoglobulin Y spike SARS-CoV-2 because IgY is specific due to it's not react with the remote factor and didn't react with the protein A and protein G. And this IgY will bind with the SARS-CoV-2 RBD because SARS-CoV-2 RBD is the part of the spike protein from the SARS-CoV-2, and it could bind specifically with the IgY spike SARS-CoV-2 due to the antigen and antibody binding, specific binding. There's actually two most common methods that we can use for the conjugate, the gold nanoparticle and the antibody. It is the direct conjugation and the covalent conjugation. The direct conjugation is the most used one because of its simplicity, but it has a couple of drawbacks such as high antibody concentration needed, easily distracted by pH and ion, and it has a poor stability. And for the covalent conjugation, less antibody needed, good stability, and it more stable from the pH and ion factor. But it's more difficult to do due to its more step to do for this research, and it needs extra material. And in this case, it is the 3-MPA or 3-mercaptopropanic acid and EDC-NHS or EDC-NHS. And so we will optimize this 3-MPA and EDC-NHS. And for the direct conjugation, we will optimize the pH and the ion. Or in this case, we will optimize the pH and the buffer usage. And this is the methodology for this research. First of all, we'll synthesize the gold nanoparticle, and then we'll optimize the pH and the buffer for the direct conjugation, and we will optimize the 3-MPA and EDC-NHS concentration for the covalent conjugation. And we will, after the optimization, we will conjugate both of them. And after that, we apply them in the lateral flow assay to detect the RBD of SARS-CoV-2. This is the result for the gold nanoparticle that we synthesized. As we can see in the figure 1A, it's the spectrum of the gold nanoparticle, and the 1B is the histogram of the size distribution for the gold nanoparticle. As we can see from the figure A, the gold nanoparticle has the OD or optical density of 1.06 with the wavelength of 522 nanometer. And for the size distribution, it's actually a bit wide from 27.45 to 57.09 nanometer, with the 39.58 nanometer as the most frequent one with the frequency of 27.55%. And the next is the result for the pH and buffer optimization. And we use a couple of buffers such as trisma, borate, and bicarbonate with the various pH. As you can see, the figure A is the spectrum of pH and buffer optimization of IgYS, SARS-CoV-2, and gold nanoparticle conjugation. And the B is after the addition of the sodium hydroxide. The sodium hydroxide is used to decrease the stability of the conjugate, so we can see which one is the most stable one. And we will choose the least wavelength shift between the bare gold nanoparticle and after the addition of the sodium hydroxide. And this is the table of the wavelength before and after addition of sodium hydroxide. And so in this case, we choose the trisma with the pH of 8.5 for the direct conjugation. And we choose the bicarbonate 9.5 for the covalent conjugation because because the trisma has a amine group which may distract the covalent conjugation. And this is the result for the 3 MPa concentration optimization with the various time from 1 hour to 24 hours. Interestingly, we can see that figure A until D, it shows no significant changes. And in the figure E, it shows significant changes after the 24 hours mark, which show it's not that stable. And for the figure F, it shows instability or poor stability even from the 1 hour mark. And so we will choose the 2 millimolar because it has a good stability with the highest 3 MPa concentration. And this is the optimization for the EDC-NHS concentration. We use the 0.01 to 1 milligram per milliliter. In this result, as we can see, 0.01 milligram per milliliter and 0.05 milligram per milliliter show a really good stability. And in this case, we choose the 0.05 milligram per milliliter due to its higher of the concentration with the good stability. And after all this optimization has been done, we conjugate both of them using direct conjugation and covalent conjugation. And this is the result of the lateral flow assay test. And figure 6A is the direct conjugation and the 6B is the covalent conjugation. And the control line consists of anti-chicken IgY, and the test line consists of SARS-CoV-2 RBD. As you can see, the control line for both figure A and figure B show a really good result, which indicate the conjugation has successfully done. And for the test line, interestingly, we could see that figure 6B is more sensitive than the figure 6A. And then we use imaging plot to see the area for both tests, the direct conjugation and the covalent conjugation. And respectively, direct conjugation and covalent conjugation has an area plot of 1,721 and 8,438, which our conclusion for this research. The gold nanoparticle and IgY has successfully conjugated using the direct conjugation and covalent conjugation. The covalent conjugation show a better sensitivity than the direct conjugation, respectively, with the area plot of 8,438 and 1,721, around 4.9-fold. It shows a great potential for the lateral flow assay development, which may help the detection of COVID-19 with the further development. And this is the references that I used. That's all that I could say. Thank you.